Hello and welcome to my channel. In this video, I'm going to show you how I build an end-to-end machine learning project from building the model, train it, tune it, make an application, and deploy on a server. I'm going to walk through step by step and show you how all this integration can build a practical application. Before further ado, let's talk about the workflow of this project. In this project, as you can see, we are going to make an application for second-hand car price predictor based on a regression models. This is an end-to-end project, but in this project, I'm not going to write modular coding based on OOPS or object-oriented programming. It is one of the simplest and easiest way for building an application based on a machine learning concept. In my next videos, I build other applications based on a modular programming coding and even build a package, Dockerizing using Docker to build a package as a container and upload in a cloud as the final application. In this project, I'm going to show the simplest way, and in other projects, I will use other techniques and methods. Like other projects, first of all, we should begin with business understanding. First, we talk about what we are going to do and why we are doing. In the next step, we go to the data understanding. We get familiar with the data. We'd be familiar with the number of the columns, what is target, and other features. After that, we should talk about exploratory data analysis, which is very important because as long as we don't know the data, we cannot build any model. Then we go to the data preprocessing to prepare the features for the application. And after that, we developed and trained the model. And then we build an application, and finally we deploy the model to use the model. Now, in terms of the IDE, I'm going to use VS Code, which is, I think it is the best IDE for, at least for data science teams, because everything that you needed are there, every libraries, packages, you can even write some command. You can create terminals. There are a lot of things. If you're going to use modular coding, however, not in this project, we should use some IDEs like VS Code because even Docker and Kubernetes, we can make every single environment and packages in VS Code. I really love the VS Code. In terms of the language, we are going to use Python version 12, which is the newest one. And for building the application, we use HTML because we are going to use the web application and use the JavaScript. For build a package and make a container, put in a server, we should use Pandas, NumPy, scikit-learn for machine learning models. We should use GUnicore because we are going to upload in a server. And we use Flask. We use Flask to build the application, to convert the whole model to the application. And for ML models, we tried linear regression, decision tree, random forest, support vector regression, CatBoost, XGBoost, and AdaBoost. During the project, as we progress, we will see which of these models performed well, and the final model is based on which of them. Before going to the project, let me show you the final demo of the project to see what we will be expecting to see at the final output of the project. So this is the final web application for the model. We have to answer some questions to understand how much our car worth to be sold. For example, what is the brand of the car? I go for my favorite brand, Audi. And what is the model? For example, Q5. And even I change it to BMW, the options is here only for BMW. Or if I go for Hyundai, I only see the Hyundai. For example, I go for Elantra. The fuel, I go for hybrid, the transmission automatic. This is the year built of the model. Go for 2018. The engine size, for example, go for 12. What is the mileage of the car? We can go for 12,000. How many doors the car has? For example, 4. And how many owners this car had before? Because this web application is for second-hand car. If I'm the only owner, I go for 1. And as long as I selected, the predict button is activated, and now I can predict the car price. The car price is 16,000 and something. Definitely, we cannot try this number as the real price because it is just a demo project. In a real world project, there might be a lot of features, but just because it is the demo of the project, perhaps the number of the features and even the reliability of the dataset might not be accurate based on a real world data. But the process is exactly the same that we are going to do. Now we can start the project. As I said before, in this project, I'm not going to use modular coding. I use the simplest way, but in other projects, I will use the modular coding based on object-oriented programming. As you can see, we have some folders here. We have a folder which is called data, and definitely our raw data is there. We can take a look at the raw data, but first let me explain the folders that we have. We have model folders. We just dump our artifacts or the pickle file in this folder. We made 2 encoders for the brand and model. We dumped the model, the final model of the project, and we saved another encoder, which is for one hot encoder. I will explain all of them during the project. Next, we have one folder which is very important, and we can have our component. We have the data cleaning process. I just worked on a Jupyter notebook because in this project, I wanted to explain my insights. If I want to explain my insights in a project, definitely the Python file is not good. Python file is good only for deployment because if we want to have and write our insights about the project, we should use Notebook to have the ability to write our insights and explanation. The next step, based on the workflow that we saw, we're going to work on exploratory data analysis, preprocessing, then we split the data, and we go for modeling, and the model is in CatBooks, we will see. And the template that our web application, the structure is written by HTML programs. And then we have application or final application, the prog file, just for making a container to put in a server. We have the README and requirement and runtime, which are pretty important when we want to make a package and convert all the environment to the server as a final application. For example, in a requirement, I wrote every single libraries that we need. If somebody needs to use this project for putting in another server, the only libraries that they need is only these libraries, because the final web application is working based on these libraries. Again, in the real world project, based on MLflow or DBS or Azure ML Studio or Azure MLOps, all these files like requirements, runtime, everything will be generated automatically. But not in this project, because I wanted to, on purpose, show you how you can build it. Let's take a look at the data first to get familiar with the data. We're going to work on these data. We have the brand, the model of the car, the year the model was built, the engine size, the fuel, transmission, mileage, doors, owner, car, and price. Definitely price is a target for this model. And just because we are going to predict a continuous number, we are dealing with a regression problem. These features are exactly the features that I show you in the web application. How many numbers do we have? We have 10,000 records. And we're going to build a model based on all these data. As you can see, we have different data types. We have label, we have categorical, we have time or the date format, and we have numerical features like integer or decimal like engine size. The first step in the project, I worked on a data cleaning process. I use pandas and numpy and scikit-learn for data test splitting. I go for the load of the data sets, and I use the function to load the data sets. The data set that we have, it's not CSV, it is the Excel file. So in that case, I use pandas for the Excel object. I make a path and load the data. We just see the top 5 rows of the data. And the first step of the project, I split the data because at the beginning of the project, I wanted to set aside the test data and worked on the training data for the rest of the model. I guess this is the best way because we can deal with this situation as the unseen data. If I want to do all the data cleaning process, the feature engineering, one-hot encoding, anything on a whole data, and after that split it to train and test, when I'm going to test the model, this situation will lead to data leakage. Because we should consider test data as the pure unseen data, as the real data that after building the application, we can deal with it. So I prefer to separate the test data set as 20% of the data set. So out of 10,000 rows that we have, I just worked on 8,000 for training and 2,000 for testing. From now on, if I call df, I'm mentioning the train data, and we split the test data for the final step of the project before deployment. Then I just check if there any extra column in this project or not. Fortunately, we didn't have. And after that, I go for columns typecasting or date typecasting. Date typecasting means if the brand is going to show the brand, so the brand should be objects. If the brand is numerical, we should deal with it. But after seeing the data types, we see the type of each column is exactly what they should be. So we don't have any issue about the typecasting. And after that, we should talk about the missing values. Missing values, specifically in regression model, should be handled. Just because in this step, we didn't know which model is the best model for the final project, we should deal with missing values. As you know, for tree-based models like random forest, XGBoost, CatBoost, AdaBoost, any boosting models, missing values can be handled somehow. But for linear regression, support vector machine, having missing values leads to a lot of problems. So in anyhow, it is best way to handle missing values regardless the model that you are going to use future. I build a for loop to iterate for each single column to see whether they have any missing values or not. Fortunately, we don't have any missing values. However, in other projects in my channel, you can find some projects that we had missing values, and based on the percentage of missing values, I apply different strategies. Then I go for handling the duplicates to see whether there is a fully duplicate rows in the project or not. Fortunately, we didn't. Now I go for sanity check. Sanity check, it is very, very important. Sanity check means if the price is going to show the price, not only the data type should be price, but also nature of the data should be price. What I mean by that is, for example, labels like 1, 2, 3, they are categorical, even though they are number. In the nature, they are not number, they're just a label. We should consider this point. So I make a list and just put all the integer and float numbers, like year, engine size, mileage, doors, owner content, price. So I make a list and put all of them into the list. And after that, based on this list, I just describe it to see what is the basic statistics for them. What's the mean? what is the maximum, what is the median, standard deviation, and so on and so forth. We can see, for example, that 2000 is the minimum year, but 2023 is the maximum year. Or for the price, we can see the minimum price is 2000 and the maximum price is almost 18,000, and other information which are pretty important when you're going to build specifically the regression model. Now it is time to talk about the categorical sanity check. Specifically for categorical, I applied the same format, but instead of the include, I use the include, I put exclude, because the categorical is everything except the number. So we have the brand, model, fuel or fuel type, and transmission. And for categorical, just making the statistical things like the mean, mode, standard deviation don't mean we should just check the unique values. I make a function to find the unique values for every single categorical columns that we have. I applied for the first one in the list. The first one is brand. We see we have only these brands, and I even sorted to don't get confused about the sorting of the values. We have Audi, BMW, Chevrolet, Ford, and so on and so forth. I applied for the second one. The second index is model. We can see we have all these models, and they are a combination of all models regardless what the brand is. But in the web application, as I showed you, we can be dependent based on a drop-down that the user selects. For the fuel consumption, we have 4 types of fuel consumptions. We have diesel, electric, hybrid, and petrol. And the last one is the type of the transmission. We have automatic, we have manual, and semi-automatic. And finally, we just make a checkpoint to push this data for the next notebook that we are going to do. Just because in this file, first we split the data. I just store all the test data for the features, for the target, and the data frame that we work with, numerical features and categorical features. I stored all of them. And later on in other notebooks, I can just call them. And I don't need to build the numeric columns or X test or Y test for the second time. Now we can go for the next step, which is exploratory data analysis. For exploratory data analysis, the library that I'm going to use is Pandas, Matplotlib, and Seaborn for data visualization, and stat models for running some statistical hypothesis tests. In the previous steps, we stored some objects like data frame, numerical columns, and categorical columns. And in this notebook, because it is totally separate notebooks, I just call them. And I don't need to make it anymore. First, we can start with descriptive analysis. For descriptive analysis, we can start with numerical data. First of all, I make a function to see the KDE, or the distribution shape of every single numerical column. We had this plot, or the KDE plot, and in this plot, I defined the mean and the median, because in this case, we can see whether a numerical column is skewed to the right or skewed to the left. If they are totally skewed, in the data pre-processing step, we should deal with this situation. We transform the data to logarithm or other techniques for making the numerical columns to somehow a normal distribution or Gaussian distribution. So I applied this function that I built in the numerical columns that we built it in the previous step, and here we just called it. You can see for the year, the dashed line is the mean, and the solid one is the median. You can see the mean and the median are pretty close to each other. It means this data is almost totally following the normal distribution, and we don't need any issue about the outlier and the transformation. We can go for engine size, exactly the same. However, engine size is not following the normal distribution. It is using the binomial. That's okay. We don't have any issue. For the mileage, exactly the mean and median are totally the same, and even for the engine size. For the doors, however, the mean is a bit more than the median. It means we might have the right skewed because the most of the data are here. The mean or the average number is a bit to the right. It means we might have some outlier, but we can check these things in the outlier section. But it seems we don't have any issue about these columns. And for owner and for the price, which is the target of the model, and it is very important compared to the other one. Unfortunately, this data is following the normal distribution. We don't have any issue. And I observed anything and I just write it down. It means we don't have any issue about any of these columns. It is for descriptive analysis for numerical. But what about the categorical? The categorical is only about the mode. We have different labels in every single categorical column, but we want to see which of them repeated more than others. For example, for brand, the Ford car is repeated more than other cars. That makes sense. In North America, Ford is much more popular than other brands or European cars. The models, Accord, I think it is for Kia, if I'm not mistaken. If I'm mistaken, please write in the comment. The fuel is electric car. It shows as we progress to the newer years, most of the people prefer to have the electric car compared to the petrol or diesel car. And transmission, that is the manual, that is very interesting because I thought most of the people would rather having the automotive, the transmission, but it seems the manual is the most popular one because it repeats more than other type of the transmission. Now we can go for correlation analysis. For correlation analysis, we have two types of correlation analysis. The analysis or the correlation analysis between all numerical columns and correlation analysis between numerical columns and price or the categorical columns and the price. For the second one, comparing the categorical columns and numerical columns, we use ANOVA test. But for pure numerical columns, the correlation between them, we use the Pearson correlation. Let's start with numerical data with the Pearson. I make a figure based on the MathLogic and Seaborn to have 3 columns and 2 rows, and this is just the dimension. And I use the for loop to iterate for all numeric columns. And for each of them, I make a regression plot. It is exactly the scatter plot, but it shows the regression line. So we can see the correlation in positive or negative. And I just put the line for the correlation line as the black one, and the dots or the data points, all of them should be red. And then I apply it, and we can see this result. For example, for the year, you can see for the year, we have, this is the correlation between all numerical columns and the price. The price is y-axis. It means as long as we progress the year, if you have the newer year, it makes sense. The price of the car is increasing. So it means they have the positive relationship with each other. And also for engine size, that makes sense. If you have a car that engine size capacity is higher, you should pay more for purchasing the car. And exactly for this one, for the mileage, we have the negative. Just because the mileage of the car is increasing, definitely the price should decrease because they have the negative correlation with each other. And definitely, there is no relationship between the number of the doors and number of the owners that the car has before. And for the price and price itself, that makes sense. So this is very meaningless because we are just comparing price with price. So, and these are my observations. You can read it. Now, again, for this comparison, I can use a scatter plot or regression plot, or I can use the heat map. In this time, I use the heat map. I applied exactly for the same columns, for numerical columns, to see what is the strength of the correlation. For example, we saw there is a correlation between year and price here, but we want to see how strong it is. And we see 66%. which is average, which is not very high, not very low. And these are all the numbers based on expert domain in a real-world project. We should talk about it as a team to see which of these columns doesn't bring that impact on a model. So let's remove it. Or in the feature engineering, we can build some features to make the model more robust. Now we can go for categorical data to see the relationship between the price as a target, as a numerical, and other categorical variables. And in this case, we should use ANOVA test. I go for ANOVA test and again make a for loop to see the relationship between the price and other categorical. For ANOVA test, I use the stat model OLS to find the relationship between those columns and the price. It is based on the p-value. Now, based on the p-value, we can see which of these categorical columns are important to explain the price, or they can bring impact or positive impact on a model. We can see the p-value between the price and model is more than 0.05. So it means the brand cannot help the model to perform well. And also for the model, I think it makes sense because the brand name or the model of the car has nothing to do with the price that you're going to purchase for a car. But for fuel and transmission, that makes sense. And as you can see, the p-value for fuel and price is pretty small. And it means these features are crucial for building the model. But just because in this project we didn't have a lot of columns, I prefer to engage brand and model as well. Now we can see, okay, I know the brand of the car are not important or the fuel is very important, but I want to see out of all those brands, out of all those type of the fuel, which of them are bringing most impact, regardless, negative impact or positive impact on the price. I just group them based on a price. I make a function to group all the data or categorical variable, and they are going to group based on a price and average of the price. You can see for the brand, out of all the brands that we have, and I just showed the top 5. Chevrolet has the highest average price among all the other brands that we have. And the next step, we have Mercedes. For the model, Equinox, if I spelled correct, has the higher price, higher average price compared to the other. What about the fuel? Electric fuel, as we saw before, because electric fuel has the highest mode, the average price is 10,000. And for transmission, the automatic has the average price. So there is a very interesting thing. We saw in the previous section that manual car is the most popular in terms of the mode. But in terms of the average price, the automatic car has the more price. It means even though people pay less money for manual car, it is most popular type of transmission car. These are all exploratory data analysis. However, you are free in this stage. You can run any exploratory data analysis, build any chart, answer any ad hoc questions, because all these questions can help you when you want to build a model. But in terms of the changing the column, this process has nothing to do with the modeling. Just in terms of the insights that you might have, your attitude about the project might change in the future. So we can go for the next step and data pre-processing. Now, in data pre-processing, I again use Pandas and Matplotlib and Seaborn, and I use the scikit-learn package as a one-hot encoder. Because in this step, I'm going to convert the categorical columns to the number. Because when we want to use machine learning models, we should convert all the categoricals to the number. However, in tree-based model like XGBoost, CatBoost, and random forest or AdaBoost, and even decision tree, they can handle the text as a categorical column, as a string, but I prefer to convert them because it prevents taking time for the modeling process. And I use pickles because I want to dump or make artifacts after building the encoder. I again call the data frame and the numeric columns. First of all, I should work on the outlier. The evaluation for this project is regression RMSE. So RMSE is super sensitive to the outlier. So if you have any outlier in the project, we should handle the outlier. So I make a function to see for every single numerical columns that I just called it, we should see whether we have any outlier or not. We can see for most of them we don't have, for year, engine size, mileage, doors, owner count, and even we saw in the exploratory data analysis when we want to see the distribution shape, we saw we don't have any outlier. However, in price we have, but this number of the outlier doesn't bring any impact or bad impact on the model. So we can go for categorical encoding process, which is very important. For categorical encoding, I had, as you can see in the model, I had one encoder for the brand, one encoder for model as a column, and one encoder as a one-hot encoder. Why I have three or two type of encoder? I will explain. I applied two type of encoding. The first one is mean target encoding. The mean target encoding is very useful when your categorical columns have a lot of labels. In this case, you can use one-hot encoding, but one-hot encoding results to have the sparse data. Because after one-hot encoding for a column which contains a lot of labels, you will have so many columns. And those columns are just one in some specific row, and for the rest, they are zero. So it leads to have the sparse data. And sparse data might bring negative impact on a model. So it's good to prevent having the sparse data. So for brand and model, I prefer to use mean target encoding. Mean target encoding works in this way that, for example, for the brand, let's talk about the Audi, my favorite brand. These techniques see what is the average price for all brands which are the Audi. For example, the average price for Audi is 5,000. Now, these techniques convert all Audi label as a string to 5,000, regardless it is for which column. In this case, we can at the same time find the average or the mean that we saw in exploratory data analysis and convert the string to the number. In this case, we prevent having a lot of columns, which is a very useful method. For the brand and model, just because in the first step in data cleaning process, we saw how many labels they have a lot of labels. So I convert them to the number as a mean target encoding. And I save them, or I make an artifact for brand encoder and model encoder. It means when we want to apply this model for the test data, we don't need to fit it. We just apply this model on the test data, and it converts all the Audi to the 5,000, for example, all the Mercedes to 10,000, and so on and so forth. So it is very useful. And also for the model, so I saved two encoders here for brand and for the model. But for two other columns like transmission and fuel, just because we have a few number of the labels, I worked on a one-hot encoder and I dropped the first one. But I dropped the first one because it is for preventing the multicollinearity. For example, for fuel, we have four types of the fuels. After applying this model, we have three columns for three types of the fuels. If all of them are zero, it means that row has the fourth type of the fuel. That makes sense. And again, I saved and dumped this encoder as a one-hot encoder. Later, when I apply this one-hot encoder on the test data, this one-hot encoder just works on fuel and transmission and just convert them and won't touch the brand and model and vice versa. And finally, I just store the data frame to go to the next step. In data splitting part, I want to again split data, but not the test. I will explain. I import the pandas and the train split from scikit-learn, and I call the data frame. First of all, I should declare what is the feature, what is the target for the model. The features are all the features except the price, and the target is the price. Here, I'm going to split my train data into two separate things. One of them is for training, and one of them is for validation. When we want to build a model, we should validate the model. But for validation, I don't like to use the test data because, as I said before, test data is only for testing and it should be considered as unseen data. So I split my data frame or the train data again. 20% of them should be for validation and the rest should be for the training data. Now we can go for the next stage, which is for model development. In model development process, I import many libraries. Pipeline, standard scaler for validation, like the cross-validation. I import many libraries like linear regression, decision tree, random forest, and support vector regression, XGBoost, CatBoost, AdaBoost, and even for hyperparameter tuning, I applied grid search and two libraries for visualization. First of all, I called the data frame that we built in the previous stages. In the first step, I make a function. I am going to apply this function for every single model that I have. As I said before, in this project, I'm not going to use modular process. If I want to use MLflow or machine learning, DevOps or MLOps, I should define this function as a folder as a utils. And whenever I want to apply this function, I can call that function and run the new experiment. And in the data flow, I can track and compare the models. But in this project, I prefer to define a function and apply this function for every single model manually. In this case, we can understand better what is the last status of the evaluation for the model. First of all, I create a fold and I split the train data to 5 sections. And this is for cross-validation because the cross-validation is very important when we want to build a model. And we define different folds or different sections and we apply the model for different sections at once. Then I create 2 variables, one of them for R-squared, one of them for RMSE. And I applied cross-validation based on a model that I will give as a parameter later for X train, Y train, and based on a fold, and the scoring is R2 because in the first one, I'm going to see what is the R-squared for the model that is applied on a train data for 5 times, and what is the RMSE. And here I just print them. After that, I fit the model on a train and test. I see what is the prediction for training, what is prediction for validation, and then I can find the R-squared for the whole model, and I just print them. And I also find the R-squared for training and R-squared for validation. Let's see. First of all, I make a pipeline for linear regression. First of all, I'm going to work on a linear regression because, as I said, I'm going to apply different models or different experiments. I make a pipeline for linear regression. For linear regression, we must not have any string. So we should scale all numerical data. And in a one-hot encoding, we convert all the values to the number, so we don't have any string. But in linear regression, we should scale the number because linear regression is very sensitive about the scaling. So I use a standard scaler and I scale all the columns that we have. And after that, I apply linear regression on a model and I put all of them in the pipeline and I say pipeline as a model. Then I bring this function that I built it. And for the arguments, the X train, Y train, Xval, and Yval validation all the same, but the model is this model that I have it. And this is the result. For R squared for cross-validation, we have 99%, or the RMS is $95. That is pretty good. But it is just for training. But about the validation? For validation, we can see they are almost the same. So it means model is not suffering neither underfitting and overfitting. That is pretty good. And even in validation, we can see RMS is even less. That it is our goal. Our goal is having the minimized RMSE. So it means so far linear regression performed very well. Now let's go for another experiment for decision tree. For decision tree, we don't need to scale data. As you saw in the linear regression, we had to scale the data because linear regression is very sensitive about the scaling data. But decision tree doesn't care the scaling the data. So I didn't put the scaling process into the pipeline. And I just add decision regression into the pipeline. This pipeline is super simple. In the future videos, we will see many complicated pipelines. And I'm applying the same concept of the same process for decision tree. We can see the decision tree for decision tree. The training R squared is 89. However, for the regression was 99. And for validation is less. Even though the validation and the training R squared for cross-validation are pretty close to each other, just because the R squared for training, not for cross-validation, is 1, it means the model is overfit. But this overfit is not very severe, but the model has overfit. And this model is not working better than the linear regression. So far, linear regression is the best model. We can go for random forest. Again, random forest, just because it is the tree-based model, I don't scale the data. And we can see we have 96 for R squared for training cross-validation, 99 for R squared for training, not cross-validation, and R squared for validation data, 96. It's not suffering any overfitting and underfitting, but compared to the linear regression, again, linear regression performs well. So we disregard the random forest because in this project, our criteria is RMSE, not R squared. The RMSE is $95. But for random forest, RMSE is $627. That's not good. Now go for support vector machine. For support vector machine, we got the worst result. Even R squared and RMSE are so bad, so we disregard the support vector machine for this project. And for XGBoost, even though XGBoost is a tree-based model, it is suggested that have the scale data for XGBoost. We have 99 for R squared, and we have 99 for validation. And even it is pretty close to linear regression. It's in 99, 91, 99, 20. But just because the RMSE is worse than the linear regression, we have to disregard XGBoost. But what about the CatBoost? I apply CatBoost, and you see the result for the CatBoost. The RMSE is 99.99 for training and 99.97 for validation. It means this is the best model. It doesn't have any overfit and underfit because the training metrics and the validation metrics are pretty close to each other. So it means we don't have overfit and they are very high. We don't have any underfit. And also in terms of the RMSE, which is our criteria, we have 13. That is much better than the linear regression. So we disregard linear regression, and so far CatBoost is the best model. Now the last model is AdaBoost, and we didn't have any good result. So for model selection, we know the CatBoost is the best model. So again, we ran the whole process that they built it for the function here to have the final result for RMSE and R2 for CatBoost. Now it's time to see whether we can improve this result or not with hyperparameter tuning. So for hyperparameter tuning, I make a grid for parameter. And just because the cat boost is the selected model, I just choose the parameters which are related to the cat boost. I make the iteration for 100 and 200. I could add more, but this is just for the sample test. I can add more 350, 400 and something. For learning rate, I put 0.01, 0.05, and 0.1 for every single iteration. What is the learning rate? Learning rate is very important. If we get learning rate so high, it means model might jump from the best accuracy, or even we put learning rate so low, model performs very slow. And for the depth, or the just because cat boost is a tree-based model, we set how many steps the model can go down for 4 level, 6 level, or 8 level at the depth. And we use the regularization coefficient to prevent the overfitting. We put 1, 3, and 5. And border count, it means how we can split the categorical. For the 32 or 64, the number of the splitting the categorical. This is the specific feature for cat boost parameters. Then I build the grid search and apply all these steps based on the models that we have to find the best result in terms of the RMSE. And I divided the project or the model into 5 folds. And after that, I fit the model on train and test. It means now the cat boost model as the best model is going to, this is the best model. It's coming from here that I built based on a cat boost. This is the default of the cat boost. So it means the result that they have, it is based on a default parameter. But now I'm going to apply every single combination of these parameters on the best model to see what is the final RMSE based on 5 k-fold. And we see the result is here. I apply, this is the best parameters that apply it, and I make a new model as a base model tuned. I apply these parameters and I apply the same model. This is the result of the tuned model, and this is result of the, where is it, not tuned model. You can see we have 49 as the validation RMSE for not tuned, but we have 78. So it means in this project, if we don't tune the model is working better based on their default parameters rather than applying any parameters on the model. So the final model is the best model, which is not tuned the model. Now it's time to evaluate the model. As you know, we have the evaluation sets. Now we can evaluate the best model on the evaluation dataset. I made the scatter plot, and you can see this is the predicted value and this is the actual value. It means just because we have 99% accuracy and just $35 as the RMSE means that most of the data except this one, they are pretty close to each other, and it means the model performs very well in terms of the cat boost model. And as you saw, even the model is not overfitting because the validation accuracy is pretty close to training accuracy and even the cross-validation training accuracy. Now we can even, this is just the actual predicted plot, we can see the residual plot. If the residual plot follows the normal distribution, it means the model performs very well. You can see the zero residual is here, and we have exactly the normal shape distribution. Means the model performed very well. And now it's time to apply the data on a test data. In the first step of the project, we separate the test data. And after that, we one-hot encoded, we scale the data, we label the data. Now we have to do all this process again to see how model predicts. It is exactly the unseen data. For the future data, we should have to do the same process. First of all, I should import those artifacts or the dumped encoder that we built in data preprocessing. One of them is for brand encoder to encode the brand based on a target meaning coding, model encoder, and one hot encoder. I load all of them based on a pickle. Now I apply all these encoder on its relevant columns in the Xtest. In Xtest, we have brand. So I make a new column as an encoded brand, and I applied or map brand encoder on a brand. It means now if I have, for example, in test data, in the brand, I have BMW. Now, based on this mapping, BMW is mapped to, for example, 2000. Because the brand encoder trained in previous, now I just applied in a test data. And in this case, we apply and we change the labels for the test data to number without any data leakage. The same process for the model. And I also might have some NA because it means perhaps in test data, we have some labels that the encoder during the data preprocessing section didn't see that label. For example, in the training data, we didn't have any brand like Volvo. But in test data, we have a brand like Volvo. How encoder can handle the situation? So it means for that one, put the overall average as the label for that price. And if you have any NA, again, put the overall average price for that one. Now it's time to encode the fuel and transmission. Fuel and transmission, I use the one hot encoder. And again, I call the fuel and transmission for the test. And I apply the one hot encoder for fuel and transmission. Now we have two separate data frames. One of them contains brand and model. One of them contains transmission and fuel. Now I concatenated all together and we didn't touch the numerical data for test data. Now test data is ready. We have the final model, we have the test data, and we apply. And you can see even the RS squared for test data, which was totally unseen data, we have 99% accuracy and just $48 for RMS. So it means the model is good generalized and it is ready to be deployed. And finally, I just dump and save model here as a final model. Now we can Dockerize or we can deploy model. In the future projects, I use Dockerize or Docker to Dockerizing the model and deploy it. But in this project, I just want to simply build an application and apply this model and use it as a web application. Now it's time to build an application. I make a file as an app.py, and I'm going to build my application here. First of all, I import pickle because I'm going to import the models that we built it. And I also import Flask. Flask is useful when we want to build a web application. I import pandas and numpy and scikit-learn for one-hot encoding, and the model is selected just because it is catboost. I just import the catboost. First of all, I make an application and make an instance, and I use Flask and I call it as a __name__. I import the models as a variable, and I use pickles and load the selected models that we just trained it, evaluation, and everything. Now we have it here. Now I should import the encoder, the brand encoder, model encoder, and one-hot encoder. The process is the same with importing the model. Now I should create two pages or two routes for the web application. One of them is the basic or the first route of the model. When we click on the web application, what we can see? We should see the index template or the first view that I just showed you at the first step of the project. It should use the method as a get because we want to upload this web application on a server, and the server should get this HTML file based on a route and based on a models that we built it, and the HTML file is this file. In this project, I'm not going to talk about the HTML. There are some CSS formats. They are just for beautifying. We have the HTML body. As you can see, in the body, I made just the description at the top of the model, and we have some drop-downs menu. First of all, it just choose the brand name and the model. I just added name of the models. They should be exactly the same based on the labels that model have, based on the process that we saw in exploratory data analysis, unique number of the values. We should have exactly the same. Otherwise, the model cannot understand this is Honda with 1A or 2As. Because 2As, it is totally the new for the model, and model cannot understand it. So it should be exactly the same based on the labels that we have. For second process, I just add two more drop-downs. One of them is for fuel, and the next one is transmission. After that, anything that user selected, based on encoder that we have, all these ones should be changed to the number, and finally the model predicts it. And after that, we have year, size engine. You can work through all of them. We have number of the owners and so on and so forth. Here, I just write the JavaScript code because, for example, I said if Audi is selected for the first drop-down menu, for the model, these should be shown because they are the model for Audi. If BMW is selected as a brand, all these models should be shown in the second drop-down menu. It's just a simple JavaScript code. And yes, this is all for the coding. And here, I said I didn't allow user to click on a predict button as long as she selects every single value. Because in this case, model cannot predict based on a null values. They should select the value for all the features. And after that, the predict button should be enabled. Otherwise, this is disabled. I will show you later. And finally, they submit the form. If I come back to the application, yes, this is the root page the model is going to see. And the next one is the prediction route. This is exactly the process that model is going to apply. First of all, I make the post because post means here some data is going to enter and after that go to the server. So instead of having the get, I use the post model. I apply the if condition. Let's review the if condition. First of all, I said define variable or columns for every single column that I have. I define the brand for if the form or the data is captured, if that value is entered in a brand, here if I go to the form, if the value is entered into the brand, if one of them is selected, store value in the brand. If data selected in model, where is model here? Selected into the model. If one value is selected into the fuel, if one of them is selected, store in the fuel, and so on and so forth. So in that case, based on every single thing that user selects, I store in their specific columns. Now I have different columns, and I concatenate all of them as an input data frame. Now I have a data frame based on the values that user selected. Now it's good time to encode the data. For numerical data, we don't touch. Whatever we allow user to add it based on the value that we have. However, for mileage, it can be anything. But for number of the doors, I just put 5. You can put whatever you want. We don't touch the numerical. But for categorical, we have to map. How we can map? Exactly, if you remember, when we tested models on the test data, it is exactly the same process. But here, instead of the test data, we have the input data that we just build it into the application. I just encode the brand, encode the model, and one hot encode the fuel and transmission, and drop the extra columns. And finally, I apply the prediction on input data, that is the final version of the data, based on a model. What is the model? Model is the best model that we stored in CatBoost untuned model, because untuned performed better than the tuned model. Now, whatever the model suggests us, I stored as an output. If output is less than 0, it means just because price cannot be less than 0, We just want to return, sorry, you cannot sell this car because the price is negative. But if this price is more than zero, we can say car is worth at any output shown here. And finally, we just debug the model and push it to the server. Okay, after all this process, I just make two files. One of them is requirements, and one of them is runtime. Runtime is the version of the Python that I want to server realize works based on this version of the Python. And the requirements means if I want to make a package from my project, server should find some libraries from my model because server doesn't know I'm going to use using the cat boost or XGBoost. So I said, okay, if I want to apply this model as a package, as an atomic package, the server should first install the Flask, pandas, NumPy, scikit-learn, why scikit-learn, because in the model we have encoder, one-hot encoder, and one-hot encoder is a library in the package of scikit-learn. And Unicore, this is mandatory for the server, and cat boost. Which version of the cat boost we use? We use 1.2.7. As I said, in this project, requirement is manually. But in the future projects, when I use the MLflow or Azure Flow, we see all this process, the requirements and runtime is generated automatically based on a version of the libraries that we use, and we don't need to add it manually. The next step is that I'm going to push all this data to my GitHub. Why? Because I want to make a connection between the server with my GitHub, not server and my VS Code in my local. So I push all the data into the GitHub, and after that, we can run the application into the server based on a connection between the server and my GitHub. Here, I pushed all the data into my GitHub. The name is deploy ML car price predictor. You can see the model is here, the template is here, and the license profile, and even the app that we made it, the requirements, and runtime. And also there is a README file. You can read this file to see all the steps that we did it, and the columns, everything. And the model is deployed 4 days ago. And I just want to show you how you can use this model. So this is a GitHub. I provide you with the link in the description below this video. There are a bunch of ways for deploying or make a connection between your GitHub and a server. You can use AWS, you can use Azure, you can use Heroku. I use the Render.io. Render.io is very super powerful, and I used it. I make a connection, just add a new, I just add a web service, and inside the web service, I said make a connection between my GitHub and which version of the Python that I use it, what is the branch of my GitHub, it was the main branch, and other requirements. You see, we should install the requirements, and it is exactly the file that we built it needs if we want to apply as a package. And GUnicorn, that was mandatory for applying to the server. And you can use any type of the features. Definitely, if you want to go for any professional way, you have to pay. I just use the hobby version just for free. So if you launch the application, please be patient to application to be launched because it is just a free server. It takes a bit 1 minute. I appreciate if you wait till application is launched totally. And after that, we can deploy the server. If we do all this process, the application is ready to launch. This is my application that I built it. This is Mehrdad car price predictor. If I go there, you see there is a link as the link of the application. If I click it, we jump to the application that we built it. Okay, now this is the final result of the project. We have the brand. It is exactly based on HTML structure that we built it, based on the features that we write it down, and they are joined to each other based on that JavaScript code that we just built it. We have the fuel consumption, whatever I choose as a user. Finally, the encoder just encoded the fuel, transmission, and brand, and the model. and the model doesn't touch any numerical variable. As you can see here, predictive disabled, because we should let users select all the features and after that apply it. For example, if I select the electric car as a transmission as the semi-automatic, the year go for 2014, the engine size, I should select it. Okay, 1.5. The mileage go for 10,000. You see, again, the bottom is not activated. Number of the doors, just 2, and number of the owners, just 3. Now the button is activated. I can predict it. You see, this car, based on those features, is worth at $11,500. In this project, I showed you how I built an end-to-end machine learning model in a simple way without any dockerizing or MLflow. However, it's not the professional way. In the next videos, I will show you how I use the MLflow and Azure DevOps to make an end-to-end machine learning and web application to build a practical application for predicting. I hope you enjoyed this video and thanks for your watching.